Chapter 12 is about non-renewable energy resources. The chapter opens up with a bunch of major oil spills that have taken place. Some of the ones that they mention are in January 1969. They refer to it as blowout. It's an oil well explosion off the coast of Santa Barbara, California, and 3 million gallons of oil were spilled. March 1989, the Exxon Valdez in the Prince William Sound in Alaska ran aground, and that spilled 11 million gallons of oil. And then in April 2010, we had the BP Deepwater Horizon, which was in the Gulf of Mexico, and that was 206 million gallons. We look at coal. Also in April 2010, there was a large coal mine explosion, and coal miners developed black lung disease, other respiratory ailments. And natural gas is considered to be a clean fossil fuel, but extraction of it is difficult. The Deepwater Horizon oil spill, which is also referred to as the BP oil spill, because that's the company that was manning that rig. The oil flowed unabated for 89 days, just continued to pour out of the ground. The cause was an explosion on the platform, probably a methane gas explosion. And July 15, 2010, the leak was finally stopped. And as I said, an estimated 206 million gallons of crude was released. Looking at just a timeline of this Deepwater Horizon spill, in September, the relief well process was successfully completed. In November, the Gulf was reclosed to shrimping after tar balls were found in shrimpers' nets. You can see in January, the Oil Spill Commission reported that problems still exist. February, there's tar on the bottom of the seafloor. Moved to July, 491 miles of coastline remain contaminated. September, the U.S. government published its final report on the accident. And in January, BP will face a maximum fine of $13.7 billion under the Clean Water Act for its Gulf of Mexico oil spill. It was several billion less than feared after a judge found the size of the spill was smaller than the U.S. government had claimed. So you can see that these non-renewable resources can also have huge environmental impacts. Taking a quick look at some of the worst oil spills in history, you can take a look, and they're sort of showing you the size of the oil drop is indicating how much oil had spilled. So although we tend to focus on the ones in the United States because they're the most prevalent to us, you can see that globally, oil spills are something that take place all the time. Two primary categories of non-renewable energy. So non-renewable is once it's used up, it cannot be replaced. The two categories are fossil fuels, which are derived from biological material that became fossilized millions of years ago. The major ones are coal, oil, and natural gas. And essentially we burn these fuels and harness that heat energy from combustion. The other category of non-renewables is nuclear fuels, which are derived from radioactive materials that give off energy. And this is harnessed by transferring heat. If we look at some of these worldwide patterns of energy use, we want to address the top three sources of energy worldwide, and that's coal, oil, and natural gas. Those are our top three energy sources. Energy in the U.S. is 355 gigajoules, which is 5 times the world's average. 20% of the world's population is in developed countries, but they use 70% of the world's energy. If we look at commercial energy sources, those are ones that are bought and sold, such as coal and oil and natural gas. Sometimes wood and charcoal and animal waste can be commercial energy sources, but typically we think of ones that are bought and sold like coal and oil and natural gas. Subsistence energy sources are ones that are gathered individuals for their own immediate needs. So you gather wood for your own immediate heating use. If we're looking at some of the energy use in the United States, the three resources that the U.S. uses predominantly are oil, coal, and natural gas. The two major outputs from energy use is work, and that's the end use of energy, such as something like transportation or industry. Waste, things such as heat, carbon dioxide, and other pollutants that are released. So the two major outputs are work and waste energy. Okay. If we look at the northern areas, they consume more oil and natural gas during the winter months to meet heating demands, and in southern areas, more electricity in summer for things like air conditioning. In 2008, the U.S. energy output was 84% fossil fuel input. The energy input was 84% fossil fuels, 9% from nuclear fuel, and 7% from renewable energy. The U.S. produces 70% of the energy it needs, and 30% of it comes from other countries in the form of petroleum imports. Certain forms of energy are best suited for certain purposes. For example, transportation, you can get further on smaller volumes of gasoline and can also be provided and cut off rapidly. So gasoline is a good fuel. If you think about fueling a car with wood or coal, they have a slow start. You'd have to get that fire going and burning before you'd have enough heat energy to actually move your car. And you'd need a large quantity of those things to keep going. To determine the best source of fuel, you need to look at things like energy efficiency. So the efficiency of the process of obtaining the fuel, but then also the efficiency of the process that converts it to work. So there's two forms of efficiency that we need to address when we're looking at that. So we also have this idea of EROEI, which is energy return on energy investment. The equation that's associated is displayed here. So energy obtained from the fuel divided by the energy invested to get the fuel. So this EROEI stands for how much energy we get out of an energy source for every unit of energy expended in its production. If we look at this diagram for coal, it illustrates how energy is lost at each stage of the process. So we can say how much energy coal produces, but we have to take into account all the energy that goes into extracting that coal, the energy that goes into transporting, the energy that goes into processing, the combustion energy, the disposal energy. All of that subtracts from the overall efficiency of coal as a fuel source. And this would be true for any fuel source. We have to take into account all of these different things: extraction, transportation, processing, and the actual energy generation. If we look at efficiency and transportation, looking at things like efficiency, we think about things like a water heater. Electric water heaters are more efficient, but you need to take into account the source of the electricity, which most of the time is coal. So fossil fuels to electricity are only 35% efficient. So you need to look at the overall system efficiency. 30% of our energy use is used for transportation. Public ground transportation is the most efficient, but it doesn't take into account things like convenience or comfort or style. So in the U.S., light trucks, a category of SUVs and minivans and small trucks, is the most popular, and they account for 50% of sales, but they get less than 20 miles per gallon. They're also exempt from emissions testing. Hybrids only account for 2 to 3% of our sales. So if we look at some of these diagrams here, if we look at how many millijoules of energy per passenger, you sort of see a passenger car is pretty high up there. If you have 4 passengers in that car, you can then take that 3.6 and divide it by 4, which then makes it one of the most efficient ways to travel. So the problem is that most of us travel solitary in our cars. We don't carpool like we should. But looking at things like air travel and motorcycle, train, bus, things that can transport many people makes them more efficient. So that passenger car does increase in efficiency once we add the number of people. If we look at electricity generation, okay, this is really important. Coal, oil, and natural gas is our primary sources of energy. Electricity is considered a secondary source because we use the coal and oil and natural gas to produce electricity. 40% of the energy in the U.S. is for electricity, but because of conversion losses, only 13% is available. No pollutants are emitted from electricity use, but there is pollution from the generation of electricity. It's more efficient to heat a home with wood or oil conversions. The less things you have to convert, the more efficient it is. So if you directly heat your house with oil, you have less steps in the process than you do if you were to use that oil to generate electricity to then use electricity to heat your house. If you look at this diagram, we need to understand basically how electricity is generated. This is an idea that spans across all of our different fuel sources. This looks at coal, but really you can replace the fuel with any other one. The coal, or the fuel, is delivered to some sort of boiler where it is burned. The burning fuel then transfers the energy to water, which becomes steam. So this whole idea that we have a boiler that we heat, we create steam. The kinetic energy in the steam is transferred to the blades of a turbine, which turns the generator, which produces the electricity. Electricity is transferred to the grid. Water is cooled in the cooling tower and then discharged. The water for thermal electricity generation equals half of our U.S. water consumption. So all forms of energy, essentially, except for nuclear, which runs differently, and solar, which runs differently, but the gist is that we want to turn a turbine to generate that electricity. So we heat a source, we create steam, the steam turns a turbine. If we're looking at energy efficiency, a coal-burning power plant is 35% efficient. If we look at something like a combined cycle, natural gas combustion turns a turbine and then also turns a steam turbine. So we can combust that natural gas and harness that to turn turbines, and then also use that same energy to heat water to turn an additional turbine. That increases that efficiency to 60%. So it's using two different processes from the same source. The capacity is the maximum electrical output, and the capacity factor is the fraction of a time a plant is operating. So we often keep nuclear and coal plants always running because it takes a while to get them to full generating capacity. Another idea that we have here is cogeneration. So cogeneration is the use of a fuel to generate electricity and produce heat. We have combined heat and power. So the steam turns the turbine, and then that steam is recycled and used to heat a building. So it improves the efficiency to as high as 90% when we use that same source. We've heated that water, it's turning the turbine and heating a building, really improves that efficiency. We're going to stop here, and then in our next one we'll go into looking at all the different fuel sources individually.